Okay, these are the two big principles. I'll start off today with that same idea that take all the forces, add them together. That's called the net force, and that has to equal to ma. So there's the idea of chapters 5 and 6. Look at those details. Then this one is more about our conservation of energy, where you take the initial kinetic, the initial potential, and that's got equal to final kinetic plus final potential plus any heat that's created along in the process. And I suppose probably a subset of that is that the total work or net work is equal to the change in kinetic energy of an object. And so that's what we kind of went through in chapters 7 and 8 here. So that was the idea. So keep that in the back of your head. And I'll spend the rest of the day then going over more and more examples. We did that all day Wednesday, and I think I told you we would do it all day today. So I hope you took advantage of that. Last Wednesday I said, all right, let's do lots of examples. You had the extra MC class on Sunday, as well as the regular MC class on Friday. We've got 2 more hours of more calculations and more examples, and then another 3 hours in lab where we do those 2 experiments that I alluded to last week of conservation of energy. One with the weight going down in an Atwood's machine, and another one with a pendulum. And in fact, if I recall right, that's where we had left off. We were kind of halfway through that problem. It was number 7, so that's where I want to pick up here today and say, all right, let's try number 7. And this is like a good one to do. We got talked about it. I think we did all of A, but not yet into B. And so let's kind of set it up again and go through A again and then on to B here. But it says here in number 7, 2 objects are connected by a light string that passes over a light frictionless pulley as shown in the figure. Well, I'll pause there because again, that's that first step. Get a good physical picture of what's going on. So here's the ceiling. Here is a pulley system, if you will. It's just a single pulley hanging from the ceiling. And as I mentioned last time, and I'll say it again, and you'll see it in a few hours, this is the lab we do. You take a pulley. Now, we don't hook ours to the ceiling. We've got our bench rods that stick up, but we're going to have our pulley. And what we're going to do then is place the bottom, which in our case will be the table, not the ground here. But they have this string that comes down over the pulley and then around something like this. And you put a heavier one up at the higher spot. So in this case, it's 5 kilograms. And I think if I remember right in the picture, that's a 3 kilograms. And then they say, okay, this is 4 meters off the ground. And as I said, these numbers are much bigger than the numbers we're going to be using in lab. But other than that, it's the same basic experiment. And also, hopefully, you'll get out of lab, and I'll explain this in lab, that we're going to do more than just figure out the energy at the bottom. We're going to measure the energy something like 20 times a second as it goes all the way down here. And so we'll just say, what's the energy, and then what's the energy, and what's the energy, and what's the energy. And the whole point you're supposed to get out of the lab is that you will see that the total energy is the same as it goes down. Yes, it loses potential, but it gains kinetic. This one goes up, so it gains kinetic and gains potential as it goes on up. Well, that's the setup of the picture. So let me come back to the question again. It says 2 objects connected by a light string passing over a light frictionless pulley as shown in figure 7. The object of mass 5 kilograms is released from rest. A. Determine the speed of the 3 kilogram object just as the 5 kilogram object strikes the ground. So there's A, and like I said, maybe I'll do this kind of quickly since we already did A in the last lecture. But if you remember, we got in a little discussion here that as this thing comes down, if we go to apply our conservation of energy here, we've got initial energy, or maybe I should write it as I've been, initial kinetic initial potential is equal to final kinetic plus final potential plus any heat or any friction that's created along the way. And I don't think we got a chance to do any with friction quite yet, but we hopefully will then today here in a few moments. But this is that idea. We got into this discussion of, well, when this thing comes down, is it right before it makes impact or right after it makes impact? And the truth is it can be either one in the sense that energy is conserved, but it's going to be nearly impossible for us to talk about after, well, not completely, but at least the first step is, because if we have this impact, then there would be some friction, some heat or some impact heat that's created there. So our argument for A was, let's do the point right before. And so its height is essentially 0, but it's still moving. The other thing I wanted to point out, and I think you know this and haven't forgotten it, is remember, when we're dealing with gravitational potential energy, you can still choose y equaling 0 anywhere you want. So I was doing it in blue, so I'll do it again and say, okay, where do you want to set y equal to 0? And at least last time you guys said, let's put the ground here at y equals to 0. And I said, I agree with that what I like to do is I like to find the lowest spot and most likely call that y equal to 0 so everything is positive. And why the lowest spot? Well, that way all my numbers are positive. Why maybe why do I say probably? Because I like to make sure that that's part of the equation, because I like to have zeros show up in my equation. They make my equations a little bit easier. And so watch what happens when we do that. If we start off at the beginning, we can say we have two objects, each of them starting at rest, as you pointed out last time. And so this was the first problem we had done with two objects. And so I was picking this one to just kind of clue you in. Remember that, it's conservation of total energy, and so it's not only kinetic and the two types of potential that we've dealt with so far and heat, but it's also all the different objects that are involved. So don't forget the different objects. So we've got the two objects. We've got this one, and I put 0 for them. Then I would even put one more 0 saying, what is the mgy for that one? Well, when it starts, it of course is at ground level, and so it's y equals to 0. And so, again, just like we put in here last time, the only energy I really get here is the 5 kilograms, the 9.8 meters per second, and a height of 4 meters. That's the energy that I start with. So, going back to that same equation we did on Wednesday, it's 5 times 9.8 times 4, and this then is 196 joules of energy that it starts with. Then, of course, when you release it, it's going to go down, 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 down. And so at some point, and I think last time we did this in blue, we said, all right, now the 5 kilogram object is going to be down there, and the 3 kilogram object is going to be up here. And so now if we apply our conservation of energy on this side, we would say we have a 1/2 times 3 v squared and a 1/2 5 v squared. And I know I asked it last time, but as we're getting started here, I should ask it again. How do the speeds of these two compare? Yeah, they are the same. All right. We'll do a little harder one next where we'll still have two objects not the same speed. Then the potential energy, well, the 3 obviously went up. And so this should be 3 times 9.8. And I'll ask it again, and I think this is about where we left off last time, is the 4 is how high it would go. So in other words, if the 5 goes down 4 meters, the 3 kilogram goes up the 4 meters. And so that fits the whole strategy I've been saying. Do you got that good physical picture of what's going on? I mean, that was an important step here, to realize the speeds were the same, to realize the height's the same, to realize I'm calculating a speed before the impact, because I'm saying the heat is 0. And so all those are important decisions. Other than that, the plug and chug stuff and the math stuff is pretty straightforward. But it's those more important decisions about the physical picture and how it relates to the math, what's going on there. And I think that's it, right? Gravitational. There's no springs. There's no heat here, and so now we can begin to solve the problem. So I'll take this and subtract off 3 times 9.8 times 4. So I'll subtract that. This is a 1.5 and a 2.5. So that's really together a 4v squared if I put all of that together. So now that I've subtracted, why don't I just divide that by 4? And then finally take the square root to get the speed. And so there's a bunch of math. But I'm pretty confident that it's not the math issue that's going to give you a hard time. It could. I don't want to belittle that, but usually at this point, if you can set up the equation, know which basic physical principle we're using and put it in, you can usually get that speed. And I think that's as far as we got. Anybody? No? Did we go as far as B?
All we did was the left side. We didn't do the right.
Oh, we didn't even do this much.
We got to, you finished the first equation, but what we did was the 91, 96 joules.
Okay. So I didn't actually do the math, huh?
You didn't finish the velocity.
Yeah. Okay, so here's where we start new. It's like, okay, so what is then the velocity? So we've answered that question after a couple steps here in math and say, okay, there is the velocity. Now the problem kind of changes a little bit, or at least our view of the problem changes. Because look at in the next part of this, B. Find the maximum height to which the 3 kilogram object rises to. Well, isn't it 4 meters? No, it's not 4 meters, is it? So what happens? Okay, good. Well, okay, and I'll answer that question about the kinematic equations here in a second here. But you guys got the right idea that there's more to this. And what begins to happen is really going to require you, again, to come back and say, do you have a good physical picture of what's going on? Because what ends up happening is something along these lines. That it comes down, and then this guy is moving very fast, hits the ground, and all of that impact right there becomes some heat upon impact. And then what happens to this guy is the key. Doesn't it continue on up? And so the string becomes kind of loose or slack, if you will. And so it continues up for some distance. We don't know how high. That is the question. How high does it go? I'm going to go with the assumption that the author is saying, though, it doesn't go so high that it hits the pulley and ricochets off and bounces and stretches and makes the string, and something more complicated than that. I think he's saying, look, just the pulley is high enough up that it goes up a certain distance and then gets, kind of comes to a stop and then falls back down where it would kind of snag again and do something like this. And we don't have to go that far, but we do need to say this next step, and I'll put it in red, that what's going to happen then is that 3 kilogram is going to come up to, say, here, and the string then is going to have a lot of loose edges then, and really not be part of the problem anymore. And so when I come over here and say, let's do my conservation of energy to figure out how high it goes, or as somebody else said, could we use our kinematic equations? Well, certainly we could use our kinematic equations. We could go all the way back to those first 4 chapters. I mean, don't we know its speed, and from that, don't we know the acceleration is 9.8? And so either way is a good option here. Although, since this chapter is about conservation of energy, I will go ahead and do it in terms of conservation of energy. But yes, you certainly could do this one either way. And of course, as one of you guys asked last time, if this was a test question, would I care which way? And no, either way is fine. So do it whichever way you feel the most comfortable with. Unless, of course, the problem actually said, use conservation of energy to figure out how high it goes or something like that. And once in a while I do that, but kind of rare. I'll take any of the options. All right, so looking back on this problem, I would probably approach it by looking at it new. And what I mean by that is I would say, let's not think of this as a two-object problem anymore. Let's look at it as a one-object problem. And so I'm not worried about the heat that is up on impact when this thing hits the ground. I'm not even worried about the kinetic or the potential energy of this one anymore. What I do know is if I go right at the impact moment, this 3 kilogram is up here, and I would apply all of these great principles that we knew to that new situation. Which brings up a whole new question. Where do you want to call y equals to 0? And I've said that a lot, and I hope it's sinking in. You can set y equal to 0 for the gravitational potential energy anywhere you want. We get back to that freedom of choice again. Remember, we went through those equations on Wednesday and said, look, it hasn't been chosen yet. If this had been a spring, that's different. Remember, 1/2 kx squared. We have to choose x equal to 0 to the unstretched or uncompressed, what we call the natural length of the spring. But you don't have to do that for the gravitational potential energy. So I ask you, where do you want to call y equals to 0 for part B? Do you want to stick to the same one? All right, most of you are shaking your head. All right, I will. I even think that's probably a pretty good idea. It doesn't fit my general definition of where I like one of them to be 0, so they'll go away. But that's okay, because it also has another nice feature, because the problem says how high does it go above the ground. And so if I set the ground at 0, then my answer for the problem is the same as the answer for the value of y. Whereas if I set y equals to 0 right here, that's kind of nice because it's going to set my initial potential energy equal to 0. And I like that. However, when I get a number, I need to realize that whatever number I get for y is not the height above the floor, so then I have to add the other 4 meters. So it's kind of a trade-off, but I was glad to see most of you were shaking your head. Yeah, let's just call y equals to 0 down here. Whoops, and I should have done that in red. So for the second part B here, let me call y equals to 0 down there, and just leave it the same. So really, the only change here is that I'm looking now at a single object. So when I come over here, I would say, all right, as we get started, and I'm looking at the kinetic energy of it, I would start off by saying that then is the kinetic energy. This is my new initial, if you will, and says, okay, right here, when this 5 is making an impact, it is 4 meters above the ground and traveling with this speed. So that is its kinetic energy. And its potential energy is the mg, and there's the vh, the 4 meters, if you're going to call the ground 0. So it does start off with an initial potential energy. But then the other side of the equation becomes something like this. When it gets to its highest point, what is its kinetic energy? Yeah, 0. So again, there we're back to that. Are you understanding the problem? Do you see the physical picture? I mean, the question is, how high does it go? So it's going to slow down, come to a stop, and then be falling back down. So its velocity is 0, which means its kinetic energy is 0. And then, of course, it is at some new height. And so we can write that as y final there. And of course, there's no heat to worry about in this viewpoint because we're not looking at the total energy of both objects anymore. We've kind of switched that here, and we've let it make impact with the ground. And so we're not even looking at that one. Obviously, we could find out how much heat was eventually created, because wouldn't the kinetic energy of this 5 become all heat now on the impact? So had there been the question about how much heat is created, that would have been fine. But again, like a lot of these problems with conservation of energy, they often turn into an algebra problem once you've plugged in your numbers. And so the integrals that came to 1/2 mv squared have already been done. And the integral that gave me my mgy has already been done. And the integral that gave me the 1/2 kx squared has already been done. Don't want to forget where they came from, because sometimes those will challenge us in some harder problems. But we don't need to usually do them again. That was the nice thing about the conservative force. And then I can just put in my numbers here. So 1/2 times 3 times 4.43 squared. Add to that 3 times 9.8 times 4. And this whole side here, and then I got 147. I'll divide it by 3, divide that by 9.8, and probably not too much of a surprise that the way the numbers look up here, but deliberately made it come out to be 5 meters. And so we're 5 meters above the ground. Or, to put another way, it continues on up for another 1 meter, which I would assume would be the same answer we would have got had we've done the kinematics that somebody suggested we do to figure out how much higher it goes also. Yeah.
1/2 v squared is actually equal to like 9.8 meters squared per second squared. Is that just a coincidence of the numbers, or is like this?
Oh, I didn't. So what is it equal? What did you say?
1/2 like 4.43. Like I just kept it as 19.6.
Okay.
And I just did 1/2, and then it comes out to 9.8 still, like meters squared per second squared. So is that just a coincidence in the numbers that it was to grab and just?
Oh, no. Well, I think it's back here. You've got the no, it's not a coincidence, because there's the 2 here. There's the distance it traveled, and or maybe it's coincidental with the 4. How's that? The distance it traveled is the 4. Then we've got the 2, and we've got another 2, and then they cancel out, giving it back to the acceleration of the 9.8. So you wouldn't have got that if it had been a 5 or a 6 or a 7. But it's 4, yes. All right. Well, like I said, I hope that one makes sense. And like I said, we're going to do that one in great detail again. Let's try another one. Very similar, 2 objects. One that hopefully will force you to think a little bit more about the physical problem. Let's see, that was 7, I believe. So number 12, let's look at it. It's a movable pulley one. We saw one very similar to this in chapter 5, where we had the movement of a block around a pulley, around a movable pulley, and we have that again. Let me just read it through. The system shown in figure 12 consists of a light pulley and an inextendable cord, a light frictionless pulley, and blocks of equal masses. And maybe I'll stop there and give you the picture that they have. They've got the ceiling up here. And then they hang a pulley, so that pulley can't move. But then they put a block, and I'll call it block A, or they call it block A. And then the string goes over the pulley and around another pulley and ties back to the ceiling. But in this case, or let me give myself a little more room here, but this pulley has a block B Block B, they're saying, is identical to block A. But they're trying to say here that this pulley can move. And I hope you see that in the picture. But I'll keep reading because I don't think we're quite there at that first step, a good physical problem yet. It says here, and I'll start at the beginning, it says the system shown in figure 12 consists of a light, inextendable cord, light frictionless pulleys, and blocks of equal masses. Okay? It is initially held at rest so that the blocks are the same height above the ground. And I don't have a ground on here, but maybe that will help. But again, A and B are at the same height. They're identical blocks. The blocks are then released. Find the speed of block A at the moment that the vertical separation of the blocks is h. All right. Well, I think we better talk about this. I'm not sure I still have the good physical picture yet in my mind. I mean, if they're equal weights and I let them go, don't they just hang there? No? Okay, good. So you remember the double tension one, the movable pulley from chapter 5 there. Yes, they are not going to remain stationary. One is going to go up, one is going to go down. Which one goes up? Yeah, B goes up here. And so if we call T the tension in here, looking at the free body diagram for A, we've got A being pulled down by mg but lifted up by T. Whereas looking at the free body diagram for B, B is being pulled down by mg, but as you guys noticed correctly, good, it's being pulled up by 2t, right? It wraps around, and so you get a t here and a t there. And so B is being pulled up with twice as much as A. So, as you correctly said, that would probably tell me that B is going to go up. And if B goes up, what happens to A? Yeah, it goes down. So looking at it in terms of forces, not energy yet, but that is the point of the problem here in a second, is to look at it in terms of energy. But looking at it from our older stuff, in terms of forces, I can see that the upward force on B is more than the upward force on A. And realizing then that if B goes up and A goes down, then what that tells me is mg is greater than the tension, right? And that's the whole reason A goes down. But then likewise, 2t is greater than mg, right? And so it gives me a little bit of information about tension. This is saying the tension is greater than half the weight. And this is saying the tension is less than the weight. And so the tension is somewhere more than half the weight, but less than the total weight. That would be the explanation of why 2t would be enough to lift it up, and 1t wouldn't be enough to lift it up. Now, I'm not even sure that that's all that helpful in what I'm about to do, because we're doing conservation of energy here. But it does fit in that general first step. You got a good physical picture here of what's going on. And it sounds like you do. You've got these two blocks. You've got them both moving. And as they start to move, the one, which you've already said is B, goes up. And so maybe in blue, I will draw what will happen next. Well, I guess A is going to come down to here, and B is going to go up to here somewhere. Now the string will look something like this. And once they do that, they begin to separate from each other. And that's where the question comes in, right there. They will be separated. They started at the same height. Now they're separated with B going up, A going down, and that's really the question. It says, find the speed of block A at the moment the vertical separation is h. Okay? So obviously it's a symbolic one. And it does involve heights, and it does involve velocities. So that's the key, right? You do a problem. Are you going to do it by energy? Or are you going to do it by tension? How are you going to make your decision, especially on a test?
Could you do forces, but then you do VR, and then VR being H?
Could you? Yes. Should you do it by forces? When do we want to do forces and acceleration?
Last time.
Time, right? When do we want to do energy? Distance. And we have distances here. So there's a very good chance that we want to do it by energy. And you said it best. Well, it's in chapter 8, so it's got to be energy. Okay. But that's not going to help on the test. You know, you got to make that decision. Certainly won't help on the final exam. We'll cover so many topics by there. But it is an energy one. So pay attention. That is about distance. It is about height. So again, writing this down, initial kinetic plus initial potential must equal then final kinetic and final potential plus any heat that's created along in the process. Now again, haven't had any friction yet, no heat, other than that last one kind of had that impact, but didn't really come into play since they didn't ask about that one. Well, this one too, no friction. They said these pulleys are frictionless, so we'll just put a 0 right there. And as we start to work it out, we can start off with, well, they each start from rest. So the kinetic energy is 0 at the beginning and for each object. So I've got a 0 and a 0, and I'll put that. And then we run into that question again. Where do you want to call y equal to 0? We've got to calculate the gravitational potential energy. Any thoughts? Okay, I heard a couple people say the floor, and I should say, of course, you can't pick it wrong because you can pick it anywhere you want, but I would stay away from the floor. I'm just adding more variables because then we would have to have a variable, well, how high is it from the floor to this block, and then, you know, that kind of thing here. Okay, so I heard somebody else say, how about where they each start? All right. That's got its good and bad. I mean, its good is that both of these would then fit here with an initial energy of 0, right? And I kind of like that because I like zeros in my equation. Although what I'm usually not too crazy about is then I'm going to have a negative energy. And so the negative energy here becomes equal to the positive energy there. So, you know, I don't mind if that's what you want me to do. I got to admit, my kind of thinking was maybe here, but then that only gives me 1 0. So, what do you guys want to do? Who wants here? Who wants here? Who wants here? All right, well, it looked like a lot of you were doing this one. So maybe I'll do that one then too. All right. It's hard to tell here. But again, please understand, it's your choice. And I would even add this, when you're working on the test, make it pretty clear what you're doing. And part of it, of course, is for me so that I don't miss something and score you lower than you really deserve. But the other part is, I find that if you just do that, you do it for yourself real clear. You make it real clear, and you end up doing better on the problem than you would have done otherwise. Because I can figure out by looking in the equation. When I look at the equation, if I don't see it on your graph and on your picture, if I don't see where you called y equal to 0, the first thing I do is jump into the equation and go, all right, well, here, because they put a certain value here, this is where they must be calling y equals to 0. And then if I look to the other side of the equation and it contradicts your y equal to 0, then I see why they don't have the right answer. I mean, clearly they've messed up their definition of y equals to 0. But I know that as I'm grading it, I will quickly look for that. Whether I see it in your diagram or whether I see it written out in the equation, hopefully they will be consistent all the way through, and you'll get a full 20 out of 20 on the problem. But do yourself a favor, and like I said, also allowing me to give you as much partial points as possible. Make it real clear what you're doing over here. All right. Well, a bunch of you, it was hard to tell, but looks like you guys were kind of undecided. But a lot of you were picking that as y equals to 0. So, and that was kind of a bunch of people's first reaction. So I'll go with that and say, all right, if I do that, then what I end up with is a 0 total amount of energy to get started. They're not moving and they have no height. And so the total energy is 0. So then you can kind of see from that perspective what begins to happen is A goes down, losing energy, becoming negative, if you will. And so B comes up and becomes positive, at least in terms of potential energy. They're both moving, so they both have positive kinetic energy, which is why then on the other side of the equation, I would have something that would look like this. Final kinetic energy of the first one and final kinetic energy of the second one. Final potential energy, and maybe I'll even put G for gravitational potential energy of the first one, and final gravitational potential energy of the second one. And so as we look at this, we can say, okay, let's look at the first one. Now the first one, L, you know what? Maybe to be consistent, instead of me calling them 1 and 2, let me call them A and B, since that's what your author did to label them. Okay. And so we'll have kinetic energy of A and kinetic energy of B. And let me do that first. This would be 1/2 times m, and this would be the velocity of A squared. Where the other one would be 1/2 m times the velocity of B squared. Whereas over here, I would have an mg, and I would have a final height of A. And over here, I would have an mg and a final height of B. And so that would kind of be my breakdown. Right, and of course, as we said, if you're going to call y equals to 0 here, then obviously this number is a negative number now, right? What is the final position of A? Which is why I said, I like to set these problems out, and I like to look for where's the lowest spot, call that y equals to 0, and then I don't have to worry about my negative numbers. But, like I said, either one will work, and we just got to kind of, go with it. So, like I said, I would have picked here, but I'll go with the majority there on that one. Because there's still some more things about this problem that come back to what I've been saying. Make sure you got that step 1 really well. Do you got a good physical picture of what's going on? And obviously you guys did from the last chapter, and you already realized then that they don't stay stationary, that B goes up and A goes down. The reason I say all that is because how is the velocity of A and the velocity of B related? Are they the same? No. Good. You remember that one? Wasn't there a 2-to-1 ratio? Right? Well, good question. Why don't we go through it again? It would be a 2-to-1 ratio for accelerations, as we did last chapter, but it would also be a 2-to-1 ratio for velocity, and it would also be a 2-to-1 ratio for distance. In fact, that's where it comes from, distance. If you do this, if you say this goes down a distance, say, of RA, and this goes up, say, a distance of RB, the place really to begin is how is the position of A related to the position of B? Yeah, and then that's the 2-to-1 ratio. It takes a little time to kind of think about this, but you have to look at the distance here. Oops. Yeah, I guess that was right. But you have to look at how much did this move, or how much did it go up. And I'm kind of looking at the string here. If you realize that this block B went up R sub B, you'll see that the string then, which would go from here down to there, and then from here down to there, each of those would be RB and RB. So as this pulley goes up, you have a shorter distance by RB twice in the string. Where does it go? Well, it goes to this going down. So RA is going to be twice that of RB. And so there is our mathematical connection. That if this... well, hang on. Let me not get that far yet here. But if I were to just, go up, and this is what we did in chapter 6, and I got to admit, it was hard to see it then, and these are just hard to see here. They come back to that physical picture. Do you see what's going on? This pulley going up means that the string no longer comes down and then back up. It doesn't go down RB and doesn't come up RB. So if this was 1 meter, then we would have a meter of string here and a meter of string here. That 2 meters of string would show up because this dropped down 2 meters. And so the distance that block A travels is twice that of block B, although one's positive and one's negative. So I guess what I really mean here also is the absolute values of these. And I won't worry about plus or minus quite yet. That's going to come back into play, certainly. But I just want you to see that 2-to-1 ratio. So again, same thing we did in chapter 5. We saw that moving pulley system. It was a 2-to-1 ratio. Because then if you take the derivative, you've got the derivative of RA with respect to time, and then 2 times the derivative of RB with respect to time, and then again, absolute value to be technical here. But then that gives me the velocity of A is twice the velocity of B. And that's what I'm looking for here, is how is the velocity of A connected to the velocity of B. Now back in chapter 5, this was your comment that we did one more derivative. We took the derivative of the velocity of A with respect to time, and of course also got the velocity of B with respect to time. And again, technically, these are absolute values, so let me put absolute values in there. But then we get the acceleration of A, absolute value, is twice the acceleration of B. So there's our absolute value. And that was your comment. So yeah, they're all related in a 2-to-1 ratio. Because once you get distance, that was the whole lesson in the last test, right, of chapters 1 through 4. If you know distance, can't you get velocity and acceleration? Yeah, and so once we know that relationship, we can. And so we do. We start taking derivatives of them. For this problem, then, this is really what we care about here, is then the relationship in the velocities. Because they asked us for the velocity of one of the blocks, and I forget which it was. I think it was A, wasn't it? Number 12. Find the speed of A. At the moment, the vertical separation is h. So let me change everything to an a here. So I will leave this as 1/2 mva squared and 1/2 m, but in place of the velocity of b, I will say it's the velocity of a cut in half squared. So that's an important first step. that 2-to-1 ratio. They don't have the same speeds. It wasn't quite as simple as the number 7 we just did. There's a connection between those two. And now let's go on to the height. Isn't there also a height relationship between them? And you can see it back here. The absolute value of A is twice the absolute value of B, as we said. So if B goes up a meter, then A is going to go down 2 meters, right? And so there's my absolute value. Of course, now that's absolute value. So here's where it gets maybe a little more mathematically tricky. That's why I would have not picked y equals to 0 here. This is going to go down. But one of you saw this in terms of the absolute values. If you take just the absolute value of A and the absolute value of B, isn't that H? I mean, that's what they're saying here, right? Is that, hey, we're going to be separated by H. So one goes up and one goes down. So putting that together here, maybe this one here, is twice the absolute value of B plus the absolute value of B is H. So 3 times the absolute value of B is H. Or put another way, the absolute value of B is 1/3 H. As I heard one of you guys say early on, you kind of figured out the ratio. So if the ratio is 2-to-1, then this is going to go up. And so what you're saying is RB goes up 1/3 H, where block A goes down 2/3 of H. So there's a 2-to-1 ratio. One goes up 1/3 of the distance, the other one goes down 2/3. So the total is H, and the ratio is 2-to-1. And so knowing that, then we can put in our numbers here. We can put in an mg, and then our A is a negative 2/3 H, and our B is a positive 1/3 H. And so now we have our equation written in terms of H's and written in terms of velocity of A, and that which is the problem. Now we got the algebra to do. And so again, don't want to belittle the algebra here, but I'm hoping this is the easy step. This first part is that physical picture, the principle of conservation of energy, and in this case, the connection between velocity and heights, and how are the two blocks related, which comes from knowing which one goes up and which one goes down. And as you study this, fortunately, one of the first things you notice is that every term has an m in it. And so they'll cancel off there. And then we can go through and work this out. I guess I'll start here. This one's kind of nice here because they are like terms. They've got a G and an H in it. So here's my G, here's my H. But this is a negative 2/3 and a positive 1/3. So together that makes a negative 1/3. So when I bring it to the other side of the equation, it becomes a plus 1/3 GH. So that's this one here, plus 1/3 GH. Then they each have a velocity of A squared, but it looks like I have a 1/2 from here. And then I have a 1/2 and a 1/4. Well, that's a 1/8, right? So I have a 1/2 plus a 1/8, which of course is a common denominator of an 8, and that would be then a 4 and a 1, and so that's a 5. And so now, I'll give myself a little bit more room here. I can bring the 8 and the 5 over to the other side of the equation. I then have my 3 still over there. I have my G, I have my H, and that's the velocity at A squared. Doesn't look like anything cancels, bummer. So that's the best I can do, 8/15. G, I could put in 9.8, but since I don't know H, there's probably no real point in doing that. But there's the final answer after all of this, that it's 8/15 times G times whatever H is, and take the square root of that. And so that would be the height there, using my conservation of energy. Make sense? Okay. Beginning to look a lot the same. That's what I told you, right? It's that same basic principle applied again and again and again. And really the best thing I can do is just show you different examples here, because there's tens of thousands of different ones you could possibly do now, as long as you see that it's the same principle. So the good news here is you should just be able to walk into that test and know that, hey, any of those 10,000 problems, I can just plug in the details of conservation of energy. The bad news is you know that there is a high chance of whatever problems on that test you've never seen before, because there are so many options of what I can put on there. So you know what you can't just have seen the problem ahead of time. It's that you've got to know how to use the principles of conservation of energy to do that type of problem. That's the key here. I'm getting a little warm in here. I'm gonna turn this down. Hopefully the air conditioner will go on here. All right, well, let me keep trying this. Finally, we got someone with some friction here. So let's finally do one where we'll create some heat and throw that into our conservation of energy mix. And see what we have here. Let me see the number. It's I lost track. What number did I just do? 12. 14 then. And so 14, and for that matter, the next one, 15. And for that matter, 23. They all have a little bit of friction in here. This first one, though, is kind of a nice one because they say A, do it without friction, and then B, do it with friction. All right, so let me read the problem. 14 says, a 2 kilogram block is attached to a spring with a spring constant of 500 newtons per meter as shown in the figure. All right, well, the figure is a couple pages over. It looks something like this. There's a wall, and then there's a spring, and then there's a big block. Okay, something like this. And so putting our numbers into that picture, it says a 2 kilogram block. All right, so we've got 2 kilograms here, is attached to a spring with a spring constant of 500 newtons per meter. So there's our spring with our spring constant. The block is then pulled 5 centimeters to the right of equilibrium and released from rest. Find the speed of the block as it passes back through equilibrium if A, the horizontal surface is frictionless, and then B, if the coefficient of kinetic friction is 0.35. So A is without friction, B is with friction. It's a single block. It does have a spring. It doesn't have any gravitational potential energy, so you can see why I picked it as the first one with some friction on it. It's the easiest problem we could probably do, and still have some friction without worrying about it going uphill or downhill. That'll soon change here. But what the idea here is, let's look at A, and maybe we should draw a little picture, make sure we got a good physical picture of what's going on here. If I call this the center of the block, the equilibrium here, what they're asking us to do is to pull it over And did I remember right? Did it say 5 centimeters? So be careful with your units. They're going to play that game again with us that we saw in a couple of the other problems last time, is watch your units. Be careful what they are, and that's going to bring us all the way back to chapter 1, paying close attention to our units, and if we've got to do some unit conversion, and we will, because our energy is in joules. Joule is a newton and a meter, and so there's a meter, and a newton has a kilogram in it, and it also has a meter in it, so we need all of our joule energy, things to be listed in kilograms and meters and seconds. So maybe I should just right away put 0.05 meters there and just do my unit conversion right away and say, okay, this is how far over it is in meters, and I want to do everything in meters and in kilograms and in seconds, so everything comes out to be newtons and joules. So there's our first point. But the problem says find the speed when it gets back to equilibrium. So again, saying the initial kinetic energy and the initial potential, thank you, equals final kinetic and final potential plus any heat that's created along in the process. I'll do the same thing in a minute for B here, but for A, I'm just going to put a little X there. Okay, no friction at this point. They say, okay, what is it going to be at speed when it gets back there without friction? Well, this is a lot easier than some of the other ones we were just doing, so I think you can do this one pretty quickly. I would start off by saying, all right, what's my initial kinetic energy? Right, 0. They say pull it to the right, you release it from rest. Okay, so that was the key. Again, notice they didn't say it starts with the initial velocity of 0. Wouldn't it be a lot easier to say the kinetic energy was 0 if they had told you the initial speed was 0? But you'll notice they'll never do that, all right? It's always in some words, some kind of description, some kind of connection you have to make between the real world and the math. Okay, and so those are those word problems. How about the initial potential energy? And in fact, maybe I should even just put up here, we went through this before. I'll just put a little sub S for the spring, right? There's no gravitational potential energy to worry about in this one. It's not going up or down. But it is stretching a spring. So we're going to have to worry about the spring's potential energy. So help me out. How do I get the spring's potential energy? Good. 1/2 kx squared, right? So where do you want to put x equal to 0? Should we start with x equal to 0? Can't do that, can we? Right? So this is just the opposite of that one. Where does x equal to 0? We can't choose it, right? It was chosen back when we used Hooke's law. We made that choice, and we chose x equal to 0 at its natural length. So we have no option but to use that position as x equal to 0 if you are going to use that 1/2 kx squared. So again, that's why we went through that on Wednesday. So wait, you can choose y equals to 0 for the gravitational potential energy, but if you're going to use Hooke's law, that choice has been made in the derivation of the 1/2 kx squared. So what I'll have to do is I'll have to put in the 1/2, the k is 500, and the x is 0.05, and I will square it. So that's got to be my energy. And as you guys have seen me do before, and I'm not sure why I like to do this, but even before writing out the second half, it's like, okay, if I already know that side of the equation, how much energy is that? How much do I have to work with, if you will? Because I know that won't change. That is the total. So this is 0.625 joules. And now if you think about the physical problem, I think you can see what's beginning to happen. It's sort of like a ball being dropped. Of course, this is then a spring being compressed, but as it moves in, just like a ball going down, is we lose potential energy. Where does it go? To kinetic energy, right? And so the block goes faster and faster and faster and faster, and so as we lose the potential, we gain kinetic. And in this case, no friction. So when it gets back to its center location, it is going to have a speed. And how much potential energy is it going to have? 0, because it says get back to its equilibrium, get back to its natural length. And so then I can put in my numbers. This is a 1/2, this is a 2, this is a v squared. So that made the math nice. A 1/2 and a 2 cancel off. And so I just need to do the square root of that last answer and get 0.79 meters per second for the speed. And so there's the speed without any friction. So finally we get to one here with some friction. So here's some with some friction. Let's just take a guess here. If we put some friction, do you think it's going to come back to the same speed? More or less? Yeah, it's going to be a little bit of less, sure. The friction's going to slow it down, or put it the other way, we're going to create some heat along the way. And so now the problem is initial kinetic plus initial spring potential is going to equal to the final energy plus the final spring's potential energy plus any heat that's created. So as we put in the numbers, the left-hand side of the equation is the same thing. Nothing changes there. You take the same spring, you stretch it the same 5 centimeters, starting it from rest. So this must be the same amount of total energy on that side of the equation. So that's the same. What, of course, is going to be different is right here that when it gets back to equilibrium, it will have kinetic energy, yes, like it did before, but there will be some warming of the molecules or some movement of the molecules there, and so some of the energy is in there. So given that we will have less kinetic energy, I would expect less speed. So sure, I will have less speed. So this will be a 1/2, this will be a 2, this will be a v squared, and now it opens the door. How do we calculate then the heat energy? All right, so it had been a while since we did this. Maybe it's worth working out again, but we said then that the heat was this integral of the force of friction times the distance it traveled. And the reason this one is nice is the force of kinetic friction is equal and I guess opposite. Actually, I guess we put a negative, didn't we? So that the two negatives canceled each other, but we got this idea. And we said then the simplest calculation for heat with a constant force is just force times distance. And so the kinetic friction takes us all the way back to chapter 5, and we knew it was a constant for whatever force or whatever speed. And so even though the block changes its speed as it goes along, the solid-to-solid friction is a constant number. And so that makes this a pretty easy calculation. It's just the kinetic friction times the distance traveled. Which, of course, then brings up two questions. The first one is, well, what is the kinetic friction? And the second one being, okay, what distance did it travel? Well, I'll start with the kinetic friction. Because to answer the kinetic friction, we got to go back here to chapter 5 and do our free body diagrams. And so to do problems with heat in them, I think are a little harder. That's why I kind of waited towards the end here and got the other ones and said, okay, when you start doing them with heat in there, you got to know how much friction you have. To know how much friction you have to have the normal force. To know the normal force, you got to go to the free body diagram. And so taking us all the way back to chapter 5, what I would have then is the normal force up, I would have mg down, and I would have the Hooke's law, the force from the spring, pulling it inward. Not worrying about the x direction, but just looking at the sum of the forces in the y direction, which have to equal mass times acceleration in the y direction. And maybe a nice review before the test comes up. What is the acceleration in the y direction? 0, right? It's only an x motion, so that's a 0. So I've got normal force pushing up, I've got mg pushing down, that has to be 0, and that answers the first part of my frictional component is what is the normal force. So I will put here, which is supposed to be the coefficient of friction times the normal, I can put coefficient of friction times mg. And so that was the important part of the free body diagram to find the normal force. I need the normal force to find the friction. I need the friction to find out how much heat is created. And then distance traveled. Excuse me. How far did it travel? 5 centimeters. So I'm going to put 0.05 meters. And so now we're set up to do a little arithmetic. There's the v squared. The coefficient, I think it said 0.35, didn't it? 0.35. The mass was the 2, wasn't it? Yeah, 2. Then we've got the 9.8. Then we've got the 0.05. And so, other than we've got a little bit of algebra to do, we have that velocity. So, I'll go 0.625, subtract off 0.35 times 2 times 9.8 times 0.05. And then the result of all of that, I can take the square root. And as you guys correctly predicted, it should be a little slower. Or a lot slower, I don't know. But definitely slower, depending on how much friction there was there. And then so there would be the new speed when it got back to its equilibrium. Well, how about another one here? Here's one with the crate, and I think this one is going up the hill and has some friction, or maybe it's coming down the hill. But this one has a gravitational potential energy and kind of a different normal one here. So it's number 15. If you got your book, I'll draw a picture here, but it says a crate of mass 10 kilograms is being pulled up a rough incline with an initial speed of 1.5 meters per second. The pulling force is 100 newtons and it is parallel to the incline, which makes an angle of 20 degrees with the horizontal. The coefficient of kinetic friction is 0.4 and the crate is pulled up for 5 meters. A. Well, I'll stop there. Let me draw a picture here. Okay, so it sounds like here we've got this incline. The incline is set at 20 degrees. Here's that crate. The surface is rough. We're going to end up pulling it 5 meters up. So it'll start down there and go up to here. I think it's set up. A crate of 10 kilograms. I'll put that in the picture too. So here is the 10 kilograms. A crate of 10 kilograms is pulled up. There's up. A rough incline. So there's the friction. With an initial speed of 1.5. So back here at the beginning, it's already moving. It is being pulled up with a force of 100 newtons parallel to the incline. So whatever is pulling it, this may be a cable or maybe somebody with a rope walking up the incline is pulling it. I'll put force F, but that's 100 newtons. And they're pulling also at 20 degrees, if you will. It's parallel to the incline. The coefficient of kinetic friction is 0.4. So maybe I'll put that in my picture also. So mu of k is 0.4. But there's all these variables. So we pull it up 5 meters, then A, how much work is done by gravitational force on the crate? B, determine the increase of internal energy of the crate incline system due to friction. C, how much work is done by the 100 Newton force. D, what is the change in kinetic energy of the crate? And then finally E, which is probably the main point here, is what is the speed of the crate after you pulled it these 5 meters? Okay, and that's really the idea that they're after. What is the speed of this? Will the crate still be going 1.5? Will it be going more than 1.5? Will it be going less than 1.5? How fast is this object going? Well, in this case, you can see they're cluing us in to using the work energy theorem. They're saying, okay, let's look at the work done by these individual forces. And in fact, maybe I should put a free body diagram. I may not realize quite yet that I'm going to need it here, but there is some friction. Friction means I'm going to need, the normal force. The normal force is coming back to that free body diagram. But looking at my free body diagram, I guess I would put an mg straight down. I would put a force up the incline. I would put a normal force, and then I would put a force of kinetic friction down the incline. And so again, there's our chapter 5 stuff, and maybe I should have took a little time to ask you guys again, what forces do you see? Remember, the incline is touching it, so that's the normal and the friction. Then this other object, this rope or this cable that's pulling it up, that's the other thing that's touching it. So those are the only two things touching it. So the last force then is the force of gravity. So there are our 4 forces in our free body diagram. Of course, we should probably also make a decision, how do you want to set up your coordinate system? Yeah, and so as we saw before, it seems to make a lot of sense on ones like this to say, hey, the direction it's moving or the direction it's accelerating, make that be one of your axes. And so in this case, the x-axis. So I'll say, okay, we're pulling it along the x-axis. So I have a tilted axis system, if you will, and it's going up. And so the F, the N, and the frictional force are all on the axes, but this one is off axes a little bit. And I'm not even sure how many forces I'm going to need, because the idea is to do this with energy, but I do know that part of energy is normal force, so I'm going to have to at least look at the y component here to get that normal force. Probably not the x, but probably the y. Not completely sure here. So I know this first one asked about energy. I'll start with A. How much work is done by the gravitational force? How much work? And I'll put a little gravity down here. And we could go back to the definition of work and how it's an integral, but why? Didn't we say the gravitational force is a conservative force? One thing nice about the conservative force is they're path independent. That means we could do the integral one time here in class and you don't have to do it again. So why don't we do that? Why don't we say that the work is negative of the change in potential energy? Right? That was our definition of potential energy anyways, that it was negative of the work. Because what's nice about that then is then you could just leave the minus out front and say, okay, final gravitational minus initial gravitational. And what's nice about that is we've already done those integrals. We've already said that the equation is path independent. Doesn't matter how it got there. We just need the equation at the end. These are, if you like math terms, these are state functions. And so we can just put our mg y final minus our mg y initial. And so there is our work. Oh, by the way, would you expect this to come out to be a positive number or a negative number? Yeah, why negative? Right, negative work means things tend to slow down. Positive work means it tends to speed up. And so I think you can see that something going up the hill has a tendency by gravity alone slowing down. Now I'm not saying the overall total thing slows down, because we've got other factors in here. It's not just the force of gravity, there's also the force of friction, and there's also the force of this pull on it. So it could total speed up, but gravity by itself is right here. And so I expect this to come out to be a negative number. And sure enough it is, if you go through this. I mean, the mass was 10. G is 9.8. Ooh, final position? Here's the question, what's initial position? So we haven't chosen that yet, right? So as we've been saying for the last couple of days, you can choose it once. And like the spring we did a little while ago, the x equal to 0 was already chosen. So where do you want to call y equal to 0? Okay, so right where it starts here. So maybe down on this lower edge here. So we'll call that y equals to 0 there. So I'll put that in blue. So what then would be its final height? Yeah, is it 5 meters? No, right? It's what? Yeah, I heard somebody say it. 5 meters times, yeah, sine 20 degrees. So we got to get a little bit into our geometry right here, and that goes all the way back to, our vectors of, well, I guess it was chapter 3, but really got involved in chapter 4 there. So that would be the final height. And of course, I should put here minus a 0 for completeness, but that's why you chose that initial position as y equal to 0, so that term would come out to be 0. So this first part of the question does have a negative number, and it comes out to be 10 times 9.8 times 5 times the sine of 20 degrees. And that's then 167.6 joules. It is a negative number. Let me just check to make sure my calculator was in degrees. Yeah, it was. Okay. And so there would be the work done by gravity. Negative the change in potential energy. So again, kind of a plug and chug type of problem here where we don't have to do those integrals again. And the negative number is my clue that this by itself would slow it down. Well, it goes on to determine the increase in internal energy of the crate inclined system owing to friction. Well, they use an interesting set of terms there. Internal energy, that's the heat I've been talking about gaining along there. And we should even say more technically right than what I'm using the word heat for, because what you'll discover next semester is we kind of reserve that word heat for the amount of energy that goes from one object to another, and that's not quite what happened here. But all right, but internal energy, heat, whatever you will, there's some of that energy, that Q in there. And so they're after the Q. And as we noticed in the last problem, that would be the force of friction times the distance it travels, if it's a constant force, and that's why we like to use kinetic friction here. It's a simple one to do. And so sure enough, there it is, my heat energy there. Okay. Oh, did it say heat energy or did it say work? No, determine the increase of internal energy. Yeah, okay, I guess they have the Q there. Of course, as we saw in the last one, and this was the whole point of doing these two, and the next one is, hey, if you do some heat, you got to know what the friction is. To do the friction, you got to come back to chapter 5 and do the free body diagram to get the normal for us. So this is the coefficient of friction times the normal force times the distance traveled. So let me come over here to my free body diagram and then kind of look at this and say, all right, let's look at the sum of the forces in the y direction. That has to equal mass times acceleration in the y direction. And the nice part about tilting your axis in this way is that this object only accelerates in the x direction, and I'm not even sure if it's going faster or slower yet, but I know it goes in this direction along the incline, so it does not move perpendicular to the incline, which is my y direction, so my acceleration in the y direction is 0. And so as I look at this and maybe put a little angle in here, I begin to see now, and I guess I'm wondering if I put 20 degrees in here, is that okay, or shall I go through that again here. If I've got an incline at the angle theta, and I draw a line straight down as opposed to a line that is perpendicular. So that's what this would be. Here's the line that is perpendicular with the normal. Here's the line that is straight down. What is that angle? Well, if you're looking at this first triangle, that would be 90 minus theta there. And so this one's got to be back to theta. Or put another way, this is the complement, and this is then the complement of the complement here. Because these have to add the 90, and so this is 90, and so this is 90, and so these two angles have to be the same, and these two angles have to be the same. So it is that 20 degrees. So that would tell me then that the normal force pushing in the positive y minus mg cosine of 20 degrees would be the component into the incline, and that has to equal 0. So my normal force is mg cosine 20 degrees. And so this problem is different than the last one in the sense that the normal force is not just mg. It is mg cosine of 20 degrees. And I said it many times when we were in chapters 5 and 6, but maybe it's worth repeating as we get ready for the test. Does the normal force or the tension always come out to be mg? No. There are times, but the only time it does is when there aren't any other forces and it's not accelerating. So that's not the situation we have here. So this then would be the normal force, mg cosine 20. So now I can answer this problem. So it's 0.4 for the coefficient of friction, if I remember right. The mass is the 10. G is the 9.8, cosine of 20 degrees, and it goes 5 meters. So putting all that in can answer that question, how much energy of heat do we get? So 0.4 times 10 times 9.8 times cosine of 20 degrees times 5 equals 184. 184. Maybe I'll go a decimal here, 0.2 joules there. So work done by gravity, and also how much heat energy or internal energy is formed there. Well, moving on to C, how much work is done by the 100 Newton force? Well, again, the general idea of work is our force, and this time I'll use a capital F since we're not talking about friction, but it's force dot dr. And so let's apply this to what we have here. And so this guy's getting pulled up, pulled up, pulled up, pulled up, pulled up, pulled up. Excuse me. And so the force is always along the incline. So probably the first question I should ask is, what is the angle? What is the dot product here? When I say, here's my force, here's my dr, cosine of, what angle there? And good, I hear some 20 degrees. Not right. But it's another little reason I picked this one. I seem to get 20 degrees in here a lot. It's 0 degrees. Why? Yeah, the dot product is the angle between the force and the direction it goes. So it goes up the angle, right? Up the incline. The force is up the incline. Both of those are up 20 degrees from the horizontal. So be careful there. There is no cosine of 20 degrees there. That's not what that dot product means. This dot product is the angle between those two vectors. And so they're in the same direction. So cosine of 0. Better still is they've given me a constant force of 100 newtons. And so when I do an integral of dr, I just get r. In other words, this is our simple physics 102, what's the work done? It's just force times distance. There's no components to worry about. They're in the same direction. It's just the very simple force times distance. So in this case, I've got 100 newtons, and we've gone for 5 meters, and so this would be a work of 500 joules. Notice the positive number here. What's that mean? Okay, it goes in the direction of motion, true. Go beyond that. Yeah, this by itself would make it go faster, right? And so if we didn't have friction and we didn't have gravity, if this was the only thing going on, that would make it go faster. Of course, the truth is we've got the other one. So gravity is tending to making it go slower. Friction is tending to make it go slower. But our work, our force here is trying to make it go faster. So we'll have to see which one is bigger. And finally, we get to D. What is the change in kinetic energy of the crate? And so really, we get to the meat of the problem. And then the next one, what's the speed? But it's D here that we're supposed to say, if you remember, that we had work is equal to the change in kinetic energy. And we said total work. And then if you remember, we dropped work into 2 pieces. We dropped it into its conservative and its non-conservative work. The conservative work, we said that is negative of its change in potential energy. And the non-conservative, we moved to the other side and called that the heat that was formed there. And so this is where our conservation of energy came from. The change in kinetic plus the change in potential plus any Q that was formed along the way would be our heat or our work. So in our case, what are they asking for? The change in kinetic energy. They're looking for that one. So I'll leave it alone, change in kinetic energy. And so what I have to do here is look at, and I guess I want to be, that was a whole other point in this problem. Bummer. I skipped over that way too fast. Let me backtrack here. Because the main reason I picked this one is at this point we had talked about our conservative forces. We talked about what? Well, we talked about gravity. We talked about a spring. And then our non-conservative force, we talked about that friction, right? But here we have an additional outside force. One more piece to the puzzle, if you will. And I'm not sure how you want to describe this as a conservative or a non-conservative force. Probably conservative force, but without putting a label here on it, I just wanted to make sure then that what we really have then is we have the work done by gravity, we have the work done by friction, and then we have the work done by, and I'll just label it as capital F, equals to its change in kinetic energy. And my bad, I skipped right past that. I just want to make sure you saw that, because this is the first time that we've had something that we are throwing in an additional force coming from this outside, besides the ones that we've been dealing with, which have been the friction and the gravitational force and the springs. But we do have this outside mechanism. But not really worrying about that. This is where it would come in. Which is why the author is really asking for this. He's asking you to come back and look at the work energy theorem and say, well, did you calculate how much work was done by gravity? Well, yeah. So in our case, it's a negative 167.6 joules. So that's the negative work we done. That's why I said that would be slowing it down. the work done by friction. And so maybe we should have come back up here. We said the work was the negative of the Q2. That's how we got this conservation of energy statement. We said, okay, the work done by friction, just like the negative of the change in potential energy, is going to be over here on the other side. So even though we calculated here a positive number, I'm going to put in a negative 184.2 joules. And so in both these cases, you'll see that the work done by these two is negative, which means, again, what? Those tend to slow it down. But the reason we were asking C then to do the work by this external one is this tends to speed it up. I know that because of the positive numbers. And all of that should be equal to the change in kinetic energy. And so these were the three pieces that contributed to whether this thing is going to go faster or slower. The three pieces of work. Work done by gravity, work done by friction, and work done by this external force there. And so besides the friction in here, I wanted to add that external one there. But now as you look at it, you can see whether this is going to come out to be positive or negative. And you can see that this is much more positive than these two are negative. So this whole thing's going to come out to be positive, and that tells me then that this block ends up going faster. It's going to gain some energy here. So I'll take the 500 first, and then I'll subtract the 184.2 and subtract then the 167.6 and come up with 184.2. No.
148.
Yeah, thank you. Positive, right? Yeah, whatever number I said was not what I was seeing in my face here. 148.2. All right. So there is the change in kinetic energy. And that was like I said, kind of the point of the problem. A chance to do another frictional one, yes, but in addition to that, one to say, what if you have this external mechanism, if you will. Which then leads really to the easier part of the problem, which is probably the main thrust of this. What's its new speed now? Okay, so to figure out its new speed, I got the individual work, I use the work energy theorem, and so once I know that, then I can just say, all right, well, the change in kinetic energy is this 1/2 mv final squared minus 1/2 mv initial squared. So the change in kinetic energy is this 148.2 joules, 1/2 m. Oh, this is a 10, right? And so this is my 10, and this is my final speed squared. My initial speed is the 1.5, and other than a little bit of calculator work here, I can find out then the speed. So 148.2, subtract off the 1/2 times 10 times 1.5 squared. Then dividing that whole thing by 5 and then taking the square root of all of that gives me a 5.23 meters per second after I do all the calculator work. And again, maybe I shouldn't do it quite that quickly, but just in the interest of setting up more problems and doing more problems, I guess I'd encourage you to take a couple of steps there so you don't make a mistake. Hopefully I didn't make a mistake by taking too many steps in one time. But I don't think that's where the problem is going to be, is doing those couple steps of math. The problems is more along the lines of normal force, friction, work energy theorem. What about this new force, and so on and so on. All right, well, let me try another one here. These beginning to look too much of the same. Again and again, same idea. I don't want you to be bored, but the truth is I kind of want you to go, same problem. Same boring, it's the same thing. How many times can you do the same thing? I get the point. Well, all right, let's try it again. Actually, this one's got some friction too, so it's got some heat. It's also got a neat little subtlety piece in here, so I'm going to see if you guys catch it. It'll take us back to chapter 5 here. Actually, 7 and 5 and 8 all rolled together. Number 23 says this. It says a toy cannon uses a spring to project a 5.3 gram. I'll stop right there. Grams. They're going to do that to me again, right? They're going to watch, see if I'm paying attention to my units. Okay. 5.3 gram rubber ball. The spring is initially compressed 5 centimeters. They're going to do it again. And has a force constant of 8 newtons per meter. Well, there's the per meter. I like that, but they're mixing my units. Okay. When the cannon is fired, the ball moves 15 centimeters through a horizontal barrel of the cannon, and the barrel exerts a constant frictional force of 0.032 newtons on the ball. Okay. With what speed does the projectile leave the barrel of the cannon? And then B, at what point does the ball have its maximum speed? And then C, what is this maximum speed? All right, well, let me set it up, starting with the number. This is number 23 here in the book. But it has something along the lines of this. A toy cannon, and they said it was horizontal. Whatever a cannon looks like. The best I'm going to get here. Trying to think what that end of the cannon looks like. Do they? I guess if it's a breech loader or a muzzle loader, right? And maybe, doesn't matter here. But the one I picture in my mind is this little one where you put the rubber ball in here, and so they said it's 5.3 grams, and there's a little spring back here. And then you have this little plastic stick that you put down the muzzle and you push it in. And so you push the ball back, say to here. And so the spring gets a little tighter. But they gave me that number, I think, here. Let's go back and read it. I think they said you push it back 5 centimeters. It says, a toy cannon uses a spring to project a 5.3 gram rubber ball. They say soft rubber ball. I'm glad. I don't want anyone to get hurt. All right. The spring is initially or originally compressed by 5 centimeters and has a spring constant of 8 newtons per meter. So the spring constant is 8 newtons per meter. So we push it back 5 centimeters. When the cannon is then fired, the ball moves 15 centimeters through the horizontal barrel. All right, so we push the the spring back 5, but when we fire this, it moves all the way to the end of the barrel here. And so this is 15 centimeters. Okay, so there's another 10 centimeters, if you will, of barrel before you get, after the spring stops contact. I'll move 15 through the horizontal barrel of the cannon. And the barrel exerts a constant frictional force. So there is a constant frictional force of 0.032 newtons. So yes, we have friction. Yes, there's some heat here. That's part of the problem. That's part of the reason I picked it. It's got some other neat things about it too. Wasn't the main reason. But this is going to be the question then about, okay, now how fast is it going when it gets to the end of the barrel, I think is that first question. And I'll read that first question, but I'll pause. Do we have a good physical picture then of what's going on? We load this thing. We basically use the energy from the spring to give it to some kinetic energy. I think you could probably even see, though, that as it goes the rest of these 10 centimeters, isn't it losing energy? So isn't it slowing down? So I would suspect at the end here is not the maximum speed of it, right? Wouldn't the maximum speed be earlier on back here somewhere? Because that was part of the questions later on. Not the beginning one, but that's kind of what I see in my head here. Now, the first question here is, with what speed does the projectile leave the barrel of the cannon. All right, so in A, I'm thinking, all right, we've got initial kinetic plus initial potential, and in this case, I'm going to just put a little S here for the spring. Doesn't seem to be angled up at an incline or anything, so it's not kind of like that pinball one that, as much as I enjoyed that one Wednesday, I still didn't make it to the pizza place. I was getting to play my pinball game, so I still have to do that. It was on my mind all weekend long. Oh man, I want to play that pinball game, but never did. So, and hopefully you didn't either. Hopefully you were studying the whole time, and maybe got a little bit of sleep because you knew you weren't going to get any sleep tonight or tomorrow night, getting ready for the test. Right? So you'll come in here and ace it all. But as I label this one, I'm just going to put, the spring. I said I'd put spring, and I put gravity there, but I was thinking about that pinball one we did last Wednesday where we had to have the spring and the gravitational one. This one doesn't need the gravitational one. They said it was horizontal. But when we get started with the ball, maybe I'll just put a 0. I was going to ask you what's the speed, but you load it in there. Again, that's back to that physical picture. What's the initial kinetic energy? 0. We got the spring compressed, the ball's just sitting there, it's at rest. 0 speed means 0 kinetic energy. But the spring is compressed, so it would be a 1/2, and then the K would be 8, and the distance would be 0.05 squared. And so there's my 1/2 kx squared. And I'll give you the same warning I've been giving you for a long time, so hopefully it's sunk in, is watch your units, right? For this to come out in joules, we need our distance in meters. So notice I put my distance in meters. Okay? And this then is my Newton per meter. So when I go meters squared, that together becomes a Newton times a meter, which becomes a joule. So that's that idea that I kept saying. Watch your units. Make sure you don't get tricked by the units and do your unit conversion. Back to chapter 1. The other thing is, where do you pick x equal to 0? Okay, right. The x has to be 0 with the natural length of the spring. We don't have that choice here. And so that's why I've got to pick a 5 here. I can't say that's 0 or 15. Those won't work here. Right? I've got to pick the unstretched length, or in this case, compressed length, the natural length of it. Okay, so now it works its way through. It gets fired. The spring goes back to equilibrium. The ball moves along the whole 15 centimeters. And so by the time it gets to the end of the barrel, it's 1/2 m. And same little warning there. Make sure that your mass then is in kilograms. That goes with our newtons, that goes with our joules. And so they gave me it in grams, but I don't want to put it in grams into my equation. So I'll move the decimal 3 and put it in terms of kilograms. So there's going to be the speed at the end. The spring has gone back to its natural length, so its potential energy is now 0. And then really this comes down to the frictional force and the heat. And fortunately they were nice to me here also, because this would be the frictional force times the distance traveled. And they just gave me the frictional force straight up. And I don't have to go back to a free body diagram to find the normal force like I did on the last 2 or 3 problems. I just got the frictional force right there, 3 to 32. So there's my force in newtons. Distance traveled, 10, 5, 15. Okay, it's the 15 centimeters, but I need to put it in as meters, so the correct answer there is 0.15 meters, right? And so again, it's not just how much has the spring gone back, it's how much has the ball traveled. And it's not after the spring touched it. I think they're implying here that the force is the whole time. So during the time the spring is pushing on it, there is a frictional force, and then the rest of it. And so we want the whole 15 centimeters. And so put in the 0.15. And then that's the main part of the problem, other than the fact that now we've got some calculator work to do here. I can start on this side by saying 1/2 times 8 times 0.05 squared. So that's my first term. From that I can subtract off 0.032 times 0.15. So that's subtracting off that term. Then multiplying it by 2, then dividing it by 0.0053, then getting an answer and taking the square root. And again, my disclaimer, there's a lot of steps there, so I don't encourage you to make all those steps on your calculator. I'm just doing it for us in time, and it's easy to make a mathematical mistake there. So don't do that on the exam. Write this out in a couple of steps, but if I did it right, that would be the speed of this ball then when it gets to the end of the barrel. Because then I think the problem gets a little more interesting actually here, and really kind of tests your physics of the problem. It says, where to go here, B, at what point does the ball have its maximum speed? Well, we kind of touched a little bit on this. Would it be when it leaves the barrel? No, because it's slowing down, slowing down, slowing down. But maybe the harder one to say is, would it have it right here when the spring gets back to its natural length? No. Close, but no. Why not? Okay, yeah, let's look at a free body diagram here. If this is the ball, it's being pushed forward by the spring, or at least when it's in contact with the spring. So during the time it's in contact with the spring, it's being forced. Isn't there then some frictional force? And you might even argue that there's a normal and an mg, but it turns out the vertical ones, I'm not even going to focus on those forces. But it's these forces, left and right, are the one interesting. When will this ball be accelerating? In the sense that it's going faster, accelerating, not slowing down. Right. So long as the force from the spring is greater than the force of friction, then we get a situation where the ball is going faster and faster. We have a net force that is in the traditional positive x direction. And so as long as the force from the spring is greater than friction. And so early on, way back here, when this thing is compressed, then the force from the spring, at least the magnitude of it, is kx. Not worrying about the negative sign there. So I'm sure for this to work right, it had to be designed so that when you push this back, there is enough force from that spring to accelerate it out. In other words, more than the force of friction. But what happens as the spring stretches? Doesn't the force from the spring begin to decrease and decrease and decrease? And so somewhere, before it gets back to here, I'm not sure where, I'll mark it in green, but somewhere, maybe right about here, the force from the spring has gotten low enough so that it is now equal to the friction. And at that point, the acceleration would be 0. And beyond that, even though it's still being pushed by the spring, what's the acceleration? Negative. The spring is still pushing it, but not as much as the friction is slowing it down. And hence, now the ball starts slowing down. So the maximum speed does not occur back here. Easy to fall into that trap, but it occurs back here someplace. So again, that's why I picked this problem. I thought it would be a little clever physics problem there to say, okay, when is it? So I'm glad the author wrote it. And I thought, oh yeah, that'll be a good one. That'll keep them on your toes and thinking about, okay, what's the physical picture here? So B is really done with forces again. I'm bringing us back to chapter 5. and saying, okay, where does that occur? Where does that maximum speed occur at? And as I pointed out, it would occur then when Kx is equal to 0.032 newtons. That's the place. And so now I can put in my 8 newtons per meter and solve for x. Probably explains why the author gave me a 32, because I can go 32 divided by 8 is 4. Newtons cancel off and we're at meters. So 0.4 centimeters or 4 millimeters, whichever way you want to describe it. So close to equilibrium, probably a little closer than my picture indicates here, but it would not be all the way back at equilibrium. And like I said, I'm sure that's why the author has it here, to get you to think, oh, it's not at equilibrium. It's not just the length of the barrel, but then it's also back a little bit further. Well, and then C says, then, well, so what is this maximum speed? All right. So let's do our conservation of energy here and really do the same problem we did in A, except in A we went all the way to the end of the barrel. Let's figure out how fast is it going when it's at this spot that's labeled in green there. All right, so it would be initial kinetic and initial springs potential would equal to final plus the final springs energy plus any heat that's created along the way. Now the first part of C is going to look just like the first part of A, where we start from rest, so 0, kinetic energy, and then the spring is still compressed, the 5 centimeters. And so there's my first bit of energy. 420 to that? 20, that doesn't seem right. Is that? Maybe I'll get my calculator out here. That's 1/2 times 8 times 0.05 squared. Yeah, 0.01. All right. So there's how much energy is stored in the compressed spring. Get ready to shoot the plastic ball out, or rubber ball, I guess it said. Soft rubber ball. Let me not forget soft. And then the other side here is really what I'm after. That this is a 1/2 and this is 0.0053 V squared. And so again, that much looks the same as what we did in A, but here's where it changes. Any potential energy? Well, yeah, that's the whole point, right? The whole point was to say that the spring does not return all the way back. So it has some distance. And so sure, it's 1/2 times 8 times 0.00, did we say 4? 0.004 squared there. So still got a little energy stored in there, which is why the ball, you know, at this point forward from the green back to the unstretched, it's getting a little bit of energy. In other words, it's not slowing down as much as it would when it's out here in the barrel. That definitely is going to slow it down a lot more. But in that area, there's going to be, you know, some slowing. That's why it's not at its maximum speed. But we had to give up that energy then. And then over here, we've got this force of friction, 32 newtons, times what? Oh good, I hear all kinds of answers. Is it 0.004? How about 0.05 minus 0.004? Which I heard somebody point 0.046. Right? Isn't that the distance it traveled? Okay. So again, another reason I picked this, I see students grabbing the wrong answer here. What we're looking at to calculate the heat is how much distance did it travel. And so the ball from here to there is how far it traveled. That's not the same as the x. The x is how much is the spring still compressed. So this is how much the spring is compressed, but this is how far the ball traveled. And so be careful what symbols you're putting in there and using the correct one. Then other than that, it's got a lot of more algebra to do. And again, I'd encourage you to do this in a bunch of steps. But I'll just do mine in one big shot here. So I did this, and I'm going to subtract the 1/2 times the 8 times the 0.004 squared. And whatever I get there, I will subtract yet again 0.032 times 0.046. And so that's the result. I will then multiply it by 2. I will then divide it by 0.0053. I will then take the square root of all of that and come up with a speed of about a 1.78 meters per second. I hope that's bigger than I got at the end of the barrel. Yep, it is. Good. And so that's its maximum speed there at the end of the barrel. Well, maybe we've got time for one more. Let's try this one. This one might throw a new twist at you, or maybe not. If you don't think of it as a new twist, good. You're seeing the point. Do I need to get the syllabus out again? Physics is about knowing how to apply a few powerful fundamental concepts to explain a universe of phenomena. Okay? But listen to this one in 27. And it's no doubt why the author made this a magenta problem. And remember, the color code is the magentas are supposed to be the hardest ones in the book here. But it says here that a uniform board of length L is sliding along a smooth and frictionless horizontal surface as shown in the picture. So the first thing they have is a board of length L on a smooth frictionless surface like this. So it's moving along. A uniform board of length L is sliding along a smooth horizontal plane as shown in the figure. The board then slides across a boundary where it now hits a rough surface. Okay, so I don't know, maybe this is we're sliding it along some tile and we now hit some carpet. Or maybe we just hit some asphalt. Well, let me give a little bit of room. So we'll do that. Then we hit a rough surface. Okay? And eventually it's going to, slow down here. Where'd it go here? It slides across the boundary across this rough surface. The coefficient of friction between the board and the second surface is mu k. So there is some friction here. This is going to slow it down. It's not going to be your fault it slows it down. It won't be my fault it slows it down. It'll be the asphalt part that slowed down. Oh, I shouldn't have said that. All right. Find the acceleration of the board. As its front end travels a distance x beyond the boundary. The board stops the moment the back end reaches the boundary as shown in the figure. What would be the speed of the board? So in other words, if this board comes across here and then continues on for a little bit of distance, total being the length of the board, and then comes to a stop, what is, and now I forgot the question, find the initial speed. So this is coming in at some unknown speed. And so here comes the speed of the board. All right, well, I'll start with A. A is kind of an intermediate step here. it says, find the acceleration of the board the moment that its front end has traveled a distance x beyond the boundary. So in A, they're looking at something like this. You've got the smooth part, then you got the rough part, and the board is kind of half and half, where the total length is L, but this distance here is X. So we have X amount of it, a fraction of it over the rough surface. Ooh. How are we going to figure out the acceleration? Now at this point, it's certainly not an energy problem. I mean, they specifically say, what is the acceleration? So this is going to take us back to chapter 5. But in the short time we've got here, I'll just kind of chop it here. And say, couldn't we think of this maybe as object 1 and object 2? So now object 1 is still over the frictionless part, and object 2 is over the friction part. So as we go to look at the forces on this and draw the free body diagram, I guess the first thing I would do is say, well, there's an M1G pulling it down and an M2G cutting the board into two pieces. So then there would be a normal N1 and there would be a normal N2. It looks like then there would be a friction only on the, what I would call the second piece. And so I'm not even going to call it friction 2. There's no point in saying friction 2 because there's no friction 1. But that would kind of be my free body diagram. I say all that is because if I were then to label all the forces in the x direction, there would be this negative Fk, and that would have to be equal to the M1 plus the M2 times g. In other words, the total mass. So I think that's probably the easiest piece of this problem is what is happening here is, whoops, I apologize. Trying to rush with time here. A is that the acceleration is clearly a negative. It's slowing it down. It is the force of friction divided by its mass. I mean, that's what it is. The harder part, though, is how do you get that force of friction? Well, the force of friction is the coefficient of friction times the normal. And that's kind of the key step there, is the normal is what? Well, it's normal number 2. It's the normal force on the part that's over the rough surface. It is not the total normal force. And the normal force then is what I would call the M2G over the total mass A. And so only part of this is actually over the rough part. Now, it still leaves me in a little tough spot here because this would be some kind of fraction, wouldn't it? This is M2. How much of the total mass M is over that fraction? Well, that kind of looks like a nice little algebra 1 proportionality. I mean, how much is mass number 2 compared to the total? They said the whole board was uniform, so wouldn't that be the same as how much X is to L, right? And so how much of the board is over the rough surface compared to the whole length would be the same as how much of mass is over the rough surface compared to its total mass. And so to get the acceleration in terms of x, then I would have a mu k. I would still have my g, but then I would have my x over L. And so I would replace that with my x over L. And so that would be my acceleration. There's how much acceleration I would have. Well, then they go on to say in B, and I guess we got to do this real quickly here, is that then the board continues on and comes to a complete stop. So if I do the work energy theorem, the work due to the friction is what is stopping this, it has to equal to the change in kinetic energy. The change in kinetic energy, of course, is 1/2 mv final minus 1/2 v initial squared. It has no final speed, so there is the change in kinetic energy. It is related to its initial speed. So that's the right-hand side. The left-hand side is where it's going to get more interesting here, is I got to do my F dot dr, and so that's why I needed this. There's my F. And so my F is a negative mu k g x over L. If you multiply that by m, so acceleration times the, mass is my force from my friction, then my dx is my integration from 0 to L, and I guess we're out of time. I'll let you do the integral, but I think you can see the only thing that changes is the x, so you're going to get an x squared, and you can finish the problem and find out what is the speed going to do. But since it's a variable problem, we have to go all the way back to our calculus, and we have to do the integral. And sorry I ran out of time to justify that one, but hopefully that helped in all the ones. So 2 days and counting. Actually just shy by 2 hours, so 46 hours.